So, hello and welcome everybody to our webinar today here at FRONIUS International. Yeah, the world or most of the world is still in lockdown or productivity has shut down to a certain limit. But when we look to our PV systems, they are still producing renewable energy during the day. And unless there is a issue with shading, for example, which leads to a yield loss, and so on. And actually, that's our topic for today's webinar, shading of PV systems, effects and measures that can be taken. So that's our topic, our goal for today, to talk a little bit about this. And before we start, I quickly want to introduce the team for today. So my name is Christoph Schirlinger. I'm from Team Trainings and Education at FRONIUS International. And next to me, or let's say on the other end of the line, there is my colleague Hans Pelzer. Hello, Hans.
Hello, good afternoon. All together from my home office, I'm watching you and answering your questions. Yeah. Okay.
All right. Thank you, Hans. So as you heard, Hans is responsible for the chat today. So if you have any questions during or after the webinar, just send them through, use the chat function, and Hans is then trying to answer them as quick as possible. We also take a few minutes time after the webinar to answer a few of your questions live then. Okay, but without further ado, I would say we then start with the agenda, and therefore I quickly turn off my camera so that we can focus on the slides. So what's on the agenda? So first of all, we want to talk about what causes shading in the first place and what are the effects of shading. Then we talk a little bit about a standard which is pretty much in every module right now, the bypass diode and what it's actually for. Then about a FRONIUS integrated solution, also a very major topic in this webinar. And after that, we talk about smart modules and module optimizers, the pros and cons, let's say a little bit. And last but not least, a short summary. All right, starting with the first topic, what actually causes shading? So there can be, of course, a lot of issues. For example, roof superstructures, such as dormer windows, chimneys, satellite, for example. And yeah, of course, also dirt can be the cause of shading on the PV modules, or snow, which is melting and sliding down then on the modules, trees from your ground or the neighbor's garden, and also cables, telephone cables, other cables running from your roof to the next, can also lead to a certain amount of shading on the modules. Yeah, so actually there comes the first topic we need to differentiate. Depending on the percentage of the shaded area and the frequency of occurrence of such shading, we can differentiate between a low, moderate, and a strong shading. So keep that in mind. That's our basis throughout the webinar, amongst some references and examples then. All right, then the next question we want to answer, what are actually the effects of shading? And the main topic with shading is actually that we have less yield. That's actually the biggest topic because the owner of the system has a later return on investment, which means he needs more time to get his investment back through the production of the system. So less yield is actually the basic, the main topic from shading. Of course, there are other things like damage to the modules and such things, but in modern technology right now, it's not such a big thing anymore due to bypass diodes and other standard technologies which prevent that. So actually less yield is the primary effect here. Yeah, and that's our first thing we have to consider. Good planning helps to reduce the effects of shading. That's actually the first thing we need to take in consideration. So do we need to put the PV system there? What if we move it a certain way to prevent the shading from this tree over there? Do we need the two separate modules on either side of the chimney when there is shading, for example? Wouldn't it be better to just leave them? That's what I mean with good planning, which then helps us to reduce the effects in the first place. But now a little bit more in detail, what does actually happen if there is shading? So now we have a system here with a FRONIUS string inverter, and we have connected here a PV generator. And now the question, what does happen if there is one module shaded by a tree in this example? And yet there we have the solution or the answer to this question. Actually, it affects the entire string. The entire string is affected just by shading this one module. Why is that? That can actually be answered by the simple basic rules of electronic. Let's say we have a serial connection in this PV generator, in this one string. And due to a serial connection, the power and the voltage increases from module to module, but the current remains equal. If we have now a shaded module, such in the previous example, there would be a current limitation. There would be a lower current than on the other modules. So there we would have a bottleneck, or let's say the weakest link in the chain is now determining the whole output power of the whole string. So because of this bottleneck, because of this shaded module, the entire string is affected. So actually now the question may rise, now why is there a different current at all? So actually we can answer that pretty simple with this schematic we can see here in this slide. We have here a schematic with module current on the epsilon axis and module voltage on the x-axis with different irradiation. For example, with the red line, we can see there 1000 volts per square meter, which is actually a standard test condition for every module. And with this irradiation, we would have 9 amps and let's say 38 volts. If we would have now a shaded module, we would have a different irradiation on the module. Let's say we now have only 400 watt per square meter. Then we can see a certain droppage on the current of the module. And that's actually what we can see on the bullet points on the right side. So the module current is directly proportional to the irradiation. That's what we can see here in the schematic. So the lower the irradiation, the lower the current, the higher the irradiation, the higher the current. And what we also can see here from the schematic is that the voltage is actually changing very little by different irradiation levels. I mean, it doesn't affect the system in a big way, because we talk about the serial connection where the voltage and the output power is just added to each other. So therefore, it's not the big issue in the first place, but we can still see it in the schematic. Voltage not that affected, but the current is actually very affected by a shading. So that leads us to the first basic rule on this webinar. We need to avoid shading as much as possible in the first place. So especially at times of the day with high irradiation, so at noon in the most countries, we need to make sure to avoid the shading at all. Because imagine we have in these times of a day with high irradiation, a very big difference on a shaded module and on the standard module in the irradiation in the sun, in the direct sunlight. And therefore the current droppage would be very high, and this could lead to damage on the shaded module. So especially in high irradiation, we need to make sure to avoid that. Also, the yield loss would be immense in that area. But in general, we need to avoid shading as much as possible. And that's what I meant before with do we need those modules beside the chimney? Maybe it's better to remove the heavily shaded modules in the first place. And intelligent system planning, the system design, comes into play in the first place. That's the first basic rule we need to make sure to do every time planning a system. Yeah, then of course we have situations where we can't avoid the biggest amount of the shading. Maybe we can say, okay, we reduce it a little bit, but in some way there is a little bit of shading which we can't get rid of, the neighbor's building or the neighbor's tree, something like that, which we can't affect. And therefore there are also standard measurements, standard solutions against these low and moderate shadings. And the first thing I want to talk about now is the bypass diode. It's actually a standard integrated diode with effects and profits, like I've written here, in most of the modules on the market right now. I quickly want to explain this on the schematic on the right side. We have here a standard module, 60 cells, and there we can see 3 bypass diodes on top of the module. We can also see 20 cells are connected in parallel to each bypass diode. And if there would occur a shading, like here on the bottom right corner, there is a leaf on one cell. This would mean this whole string of 20 cells would be affected, but not the whole module, because the current is bypassed by this one bypass diode on top. So actually we wouldn't lose the whole module, but only 1/3. That's actually the effect of the bypass diode. So if no shading existent, it's inactive. If there is shading, it's active and bypassing the current. So therefore the effects are, we minimize the losses. The module string isn't that hard affected than without the bypass diode. And the bottleneck effect, which we mentioned before, is minimized. And I also mentioned this before, it also protects against damage, like heat damage or something like that on the shaded cells. This is also prevented by the bypass diode. Okay, let's take a closer look on some other solutions. Starting on the left-hand side, I also mentioned the standard module structure. The bypass diode is actually standard integrated in most of the cells on the market, as I mentioned, 60 or 72 cells, and there are usually 3 or more bypass diodes integrated. On the other hand side, there is also a rise in half cell modules, and the structure is different in that way that we don't have 60 full cells. We have now 120 half cells. They are again connected 6 × 20 in parallel, and each 2 × 20 half cells are again connected to a bypass diode. So we again have this effect. If there is a shading on the bottom of the cell, the top part can still produce as normal because the bypass diode is bypassing the current. And that's actually what we can see here on the right side. We have a system with a full cell, which is shaded due to a melting snow, let's say. The snow is melting and is sliding down there. And in this scenario, we would have 0% output power because all of the strings are shaded. With the half cell, the same area of shading, it would mean that we have still 50% of output power due to the sliding snow. Reason is just the bypass diode are cutting the bottom half of the half cell of the module, and the top part is still producing with full power, in this case 50% of the total. All right, so that leads us actually to the second basic rule now. The bypass diodes are protecting against damage in case of shading and minimize the impact on yield losses in the case of low shading. We're not talking about strong or let's say moderate shading. Yeah, and also I mentioned here it's mostly integrated as standard nowadays in almost every module. Now, of course, there are some systems where there is not only a low shading, but there is low to moderate shading. I want to explain it now on behalf of an example, what we can do or which solution we can offer here for this type of shading. So we have here a small PV system on a side roof, let's say, and it's partially shaded from 8:45 to 10 a.m. And down below we can also see a daily PV production curve of this system. Let's say we have here now an inverter without any integrated solution against shading. It's just a simple inverter and the PV generator connected. There we would see a major lack of production here, a major yield loss in the morning, in this time from 8:45 to 10 a.m. Now I want to explain a little bit the FRONIUS solution for more yield in this scenario. And that's called the Dynamic Peak Manager. The Dynamic Peak Manager from FRONIUS is actually an integrated algorithm, which is integrated as standard, free of charge. It's standard integrated, and it always finds the optimal working point, even in the case of shading. So I quickly want to explain it on the schematic on the left-hand side. We can see here 3 curves. The blue line is actually the power curve without shading, and there we can see there is a obvious major power point on top of the line. It's called the global maximum power point, GMPP, and that's what the inverter is trying to operate on, because that's the highest output power of the system. If there is shading, like here on 8 or 9 o'clock a.m., there we have shading, and it's the red or black line, and we clearly can see there are 2 operating power points. And a system without any integrated algorithm wouldn't check the whole power curve to check, okay, there is another global maximum power point, a better point where we could operate on. They would stay on the local maximum power point, which is of course not optimal. So the Dynamic Peak Manager checks the whole power curve every 10 minutes and searches for the global maximum power point for more yield and flexibility. And now I want to explain it a little bit more in the example we saw before. So we have the same system, shaded system, and now with an inverter with the Dynamic Peak Manager activated, and then we would have this additional yield in here designed in the green area from the Dynamic Peak Manager. So actually the daily production curve with the FRONIUS inverter would look like this, and it would mean that we have 7% more yield with the FRONIUS Dynamic Peak Manager than with an inverter without any algorithm. That's what we clearly can see here. So over the whole year, it would mean a little bit more yield, 7%, 7 to 8% more yield with the Dynamic Peak Manager. So actually it means we have a solution there for low to moderate shading with a standard integrated algorithm, standard modules you can use there without any additional components you have to buy. And yeah, actually that's the 3rd basic rule I just covered there. So with FRONIUS Dynamic Peak Manager, it's just integrated as standard, and you have more yield achieved even with low and moderate partial shading, and no additional optimizers are necessary there. That's the 3rd basic rule there. So if it's just a standard system and there is partially shading, low to moderate, don't use additional components there. You're perfectly fine with standard modules and the Dynamic Peak Manager on. But of course, there are systems with strong shading, with heavy shading. In this example, we can see a large moving shading throughout the whole day. On the left-hand side, it's a tower, and actually this was a request from a customer, and he wanted to install a PV system directly under this tower, where the shading of the tower was covering over the whole roof. That's actually not very good. And on the right-hand side, it's also complex systems with a high amount of inclination, different inclinations, different orientations, it's also not that easy to cover with standard solutions. That's for sure. But the first rule you have to take in consideration there is, do I have to position the system there? That should be the first thought. Do I have to position it there? Wouldn't it be better somewhere else on the roof where there isn't that much of shading? Do I need such inclination, different inclinations and orientations? That should be your first thought. And yeah, now I want to cover some solutions which are available for extreme strong shading and different and complex systems. The first thing I want to mention are smart modules. That's actually just an integrated chip instead of a bypass diode, actually, within a standard module. And this integrated chip actually operates on cell level, let's say, and gets out the maximum module power, also in shaded situations. Yeah, actually that substitutes the bypass diodes, so it's also a benefit regarding hotspots. There are no hotspots anymore, which we could have with the bypass diodes. And just to mention a few manufacturers here, Texas Instruments is working on such solutions, and also Maxim. So you can ask your wholesaler, for example, there, do you offer such smart modules from Maxim integrated, for example? Yeah, and I quickly want to also take it in comparison now for you. We have here 3 systems, and we now want to check the performance at shading. So on the left-hand side, we start with the conventional panel, 3 bypass diodes integrated. We have a leaf on the bottom right corner here, shading 1 cell, which would lead to 1/3 yield loss of this module. So we wouldn't get out 250 watt, only 165. So only 66%. With a optimizer, with a DC panel optimizer, also very common these days to use this kind of solution, there wouldn't be such a big difference, because the main issue with optimizers is they can't operate on a cell level. So actually in the same shaded scenario, they wouldn't be able to get more out of the system than a conventional panel. Actually, it still would mean we would get out a little bit less energy, because the optimizer needs a little bit of energy for operating. So in this case, we also have written down only 66% are coming out of this shaded module. And on the far right, we can see now the integrated cell string optimizer. So from Maxim integrated or Texas Instruments, whatever you want. And they are actually operating on a cell level, and therefore they are getting a little bit more out of the module. In this scenario, 86% are putting out of this shaded module. Just to keep it a little bit in a performance check, let's say. Yeah, now I quickly want to go a little bit more into even more into detail on the external optimizers, because it's a very big topic right now, and I want to cover this and just give you an overview that there are not only advantages with external optimizers. And I want to begin with the first topic, and it's actually we have less yield at low and moderate level of shading. And that's actually because we have self-consumption of the optimizers themselves. That's what I meant with the slide before. So if we have no shading, low or moderate shading, if you're using optimizers, it's not a good thing, because they need some energy to work. They have a little bit of self-consumption, and they are not getting out more than with a standard system. So you have less yield, even less yield on this low and moderate level of shading. Yeah, the second thing I want to mention is that there are studies. Later on, I want to link to one of these studies, that there is a higher failure rate on these external optimizers. Just think about it. It's an additional electrical component underneath the module. Put that in the environment, heat, cold, rain, the moisture and everything. It's just an additional electrical component in high stress level. And therefore, it's just a higher failure rate in general. And therefore, you also need to consider the service. You have, of course, a increased service rate there. And if you think about a big PV system and you have to crawl into the middle of the PV system to get out one defect module there, it's not a nice thing to do. You have to demount all the modules on the path to the disabled one. So it's not a nice thing. So also need to consider that. And the last thing I want to mention is actually the higher risk of fire, because actually usually we talk about the still a very, very low chance of fire on PV systems in general. But when we compare those fires we have on PV systems right now, there is a study on this as well. There is an increasing risk of fire when we increase the number of plugs we have in the system. So actually I'm talking now about the MC4 plugs, and when we compare it to the system with external optimizers, such as the schematic down below, we can see that with these optimizers we have 3 times more MC4 plugs than with standard modules. You also need to consider that. So it's 3 times more, 61 instead of 21 MC4 plugs. And that's actually also a higher risk of fire in that case. So please also make sure to consider that when you plan the system. All right, now I want to refer to a study. I always mention it. Now I want to really refer to a study. Actually, you can find these papers in your handout. So if you look on the right side of your screen, you can click there on handouts and you can download there 2 papers. One is from FRONIUS, a study from FRONIUS regarding DC optimizers and string inverters. And the other one is from a university in Denmark, actually, from a professor, Toke Franke. And he also made a comparison of string inverters and DC optimizers. And that's what I want to reference now. So if you're interested, check out the paper. You can download it from the handout section. So back to the slide. This professor here compared different systems. On the one side, a string inverter, on the other side, systems with power optimizers. And they did different shading scenarios of the modules. For example, like in the picture we can see on the right, with wooden posts and with partly covered and so on. So there were different scenarios, and the test conditions were both the same for the systems with string inverters and for the power optimizers. So we had ground-mounted, southwest-oriented systems in Denmark with the same inclination on both systems of 42 degrees. And yeah, those 42 modules were actually then divided into those separate groups. Yeah, and what they found out in this study is actually very, very interesting. They did a full year of searching here from spring 2018 to summer 2019. And actually, when we compare the production in kilowatt hours, we can clearly see with the string inverter, we have more yield than with the other systems which have integrated the DC optimizers. So actually 2 DC optimizer systems were compared there, and both systems had less production than the string inverter. So if you compare that now over the whole year with different scenarios of low to moderate shading, we still are running better with a string inverter. Of course, there are systems, strong shadings and so on, where the DC optimizer would run better than the string inverter. But if we cover the whole year, the whole production of the whole year, we would be better up with the string inverter. If we look at the whole picture, and that's what matters actually for the homeowner also. So that's what I want to mention regarding the optimizers. Yeah, just written it down here, additional yield with string inverter systems, taking all the different scenarios into account, which says a lot in my opinion. Okay, now let's go to the summary, to the last slide, I say. So what I want to give you, the audience, is actually the first point. We always need to make sure that we do a good system planning in the first place. So we need to make sure we do the greatest possible avoidance of shading, because that's the most important point when we can avoid the shading in the first place. The second thing I want to give you is that with standard FRONIUS inverters with integrated dynamic peak manager, that's a perfect and an optimal and an inexpensive solution for most of the usage. Only when there is a really, really strong shading and so on, you would need a different solution. But for no shading, for low and for moderate shading, you're perfectly fine with standard modules and standard FRONIUS inverters with integrated dynamic peak manager. And the third point, I already mentioned it, use standard or half cell modules, because there you have the less expensive solution, you have less plug connections, we have heard it, we have a lower fire risk, and we also have less components and therefore a lower chance of failure, less susceptibility of errors. All right, then we covered the webinar now. And if you want to know further informations, just to remember it one last time, on the handout section on the right side on your screen, you can download two data sheets there, two white papers, let's say, from FRONIUS and from the university in Denmark. On our homepage, you can, of course, find installation instructions in our download rubric, and you can also find our next webinars, and you can register there. You can also find the recordings, the previous recordings on YouTube, also some how-to and installation videos you can find there. And now I quickly want to ask my colleague Hans. Hans, did we get any questions we can answer right now live?
Yes, Chris, there have been some questions. I would like to point out maybe a few of them. One question was regarding the dynamic peak manager. Is it possible to retrofit that on a system? No, unfortunately not. So you have to use one of the latest inverters of FRONIUS. This is the snap inverter range. So for example, the Primos or Sumo inverters, as well as the new generation, the Gen 24 inverters. So that's basically only on that one. Also the Galvo has got the dynamic peak manager integrated. A second question, any advice, a rule of thumb to place the modules around the chimney? Yes, basically, as also Christoph said, keep the distance 1 meter and try to make long strings in general, because you have to imagine if you have some shaded modules and you have a string only out of 6 modules, for example, then if you, as soon as one module or 2 modules are shaded, you will lose the voltage as well. And basically you could go under the minimum voltage of the inverter. And that would be, of course, not good. So try to make longer strings, 10, 15, 20 modules, and then you have less problems if 2 modules are shaded. So that's also a general rule, which is important. Then we had one question about the global and local maximum power point. Yes, that's the difference. Basically, you can imagine is that the local power point is the point with the higher voltage and lower current. The global maximum point, as of more than 50% shading of a module, is the point with the higher current and the lower voltage. In a string, it doesn't matter if the voltage is a bit lower, if I have one string and one MVP tracker, but the current is important. And we need to avoid to have low current, because the current is this bottleneck. If you have low current on one module, also the other ones have low current. So basically, this is the reason why we then, with the dynamic peak manager, monitor the whole voltage range, MVP range from time to time, and then adapt to the global maximum power point, which is higher, and this gives us the higher output. Yes, there was some more questions about the power optimizers. I think these ones we will answer as well in writing, as well as a question. Yes, winter time shedding on the lower part of the modules. Basically, we have to say as well, when there is shedding, you have one row of modules, and the lower part of the modules is shedded. So maybe just the lowest 10 centimeters of the modules. The effect would be very dramatic because, of course, you would lose all the modules then. To improve that is, for example, one solution with the half cell modules, half cell cut modules, or maybe to change the modules to the horizontal position, so 90 degrees to the horizontal position, and that would also avoid this problem. And then the dynamic peak manager will do his job and give full output as well. So this is something, whenever winter time is important as well, and usually it's important, then you can avoid this with replacing the modules the other way around, so in the horizontal position, not in the vertical position. Okay, good. I think there are some more questions which we need to answer in writings. Sorry for that. But basically, I think that's it from the moment. Christoph, I'll get you back to you, and I think you can then do the final words for this presentation. Thank you.
Okay. Thank you very much, Hans, for this live answering questions. And yeah, thank you guys very much for joining in today. I would suggest now, if you have any questions left or if anything is unanswered, just send them through. Hans and I will still stay online. We will just turn off our microphones right now and answer back by writing via the chat. And yeah, so thank you very much for joining in today, for listening. And yes, see you the next time, guys. Stay healthy and goodbye.